Memoization is an incredibly powerful technique that is used in intermediate to advanced algorithms design. It allows potentially very complex and very inefficient recursive solutions to become, well, more elegant and more importantly, much more efficient. Today, we explore a Python higher order function approach to implementing memoization. And what's cool about that is, if you do it right, you can augment any recursive function to become memoized. More on this after the break. Hello and welcome back to another Random Wednesday episode. So, memoization, it's pretty cool stuff. Now, I want to preface this by saying that while people typically talk about memoization alongside dynamic programming, it doesn't really have to be, and in today's episode, we'll try and stay away from that. We'll just take it as a generic way to optimize recursion. With that said, let's have a quick breakdown of today's episode to take a look at what are some of the things that we're going to cover. We're going to start off by talking about the basics of memoization, what it is and why we need it, before we move on to actually apply it towards Python programming. So we'll talk a little bit about higher order functions because that's how we're going to sort of work memoization into our code. And we're going to write some code such that for any given recursive function, we can augment it. We can basically inject a little bit of our own code and make it memoized. So if you can do things this way, if you're using a programming language that allows for it, this is going to be pretty powerful. Finally, we'll discuss a little bit about the pros and cons of doing things this way, as well as what it's like to generalize this technique to any recursive function. So with that out of the way, if you think you're okay with any of these topics, pop open the video description or look on the seek bar. You can always jump ahead to the next part. So yeah, let's go ahead and jump in. Let us begin with the fundamentals of recursion and memoization. Now, why do we want or care about memoization? The best way to understand this is to see what happens in a world without it. So to do that, let's talk about Fibonacci numbers, my favorite example of, well, recursive functions gone wrong. You see, a Fibonacci number is defined as such. It is a recursive relation, but more importantly, every recursive call is painful because it makes 2 more recursive calls. Those 2 more recursive calls are going to go on to make 4 more calls, which then make 8 calls, then 16. The number doubles each time it grows very, very quickly. So let's write a little bit of code to take a look at, why that's bad.
So let's start by taking a look at the Fibonacci function. So we're going to create a Python function that asks for the nth Fibonacci number. Then we'll implement the 2 base cases, which are of course the 2 cases in which n is 0. In that case, we'll simply return 0. If it's 1, we'll return 1. So these are the 2 base cases, right? These Fibonacci numbers are not reliant on any other Fibonacci numbers. That's simple. But for any other case, we'll need to calculate the Fibonacci numbers by using the 2 numbers that come before it in the sequence. And of course, the only way we can get at those numbers is to attempt to calculate them using the same function recursively. So that's all well and good, right? I could run this and I could ask for, let's say, fib of 5. What it'll do is, it'll go ahead and do the calculation by making recursive calls when necessary. Now, here's the problem. Once you ask for a reasonably large Fibonacci number, you realize that my computer chugs a bit, right? That took a couple of seconds. What I found is if I ask for a Fibonacci number that's slightly bigger, I might have to actually terminate this process because it's taking way too long. In order to understand why that happens, still going by the way, in order to understand why that happens, the easiest way is to take a look at the recursive calls that were actually made. There are 2 ways to do this, and I'll show you the simple way first, right? What I'm going to do is I'm going to just write a print statement that's just going to say we are calling fib n minus 1 plus fib n minus 2. Now, in case you're not sure what I'm doing here, this is a pretty interesting way to write code in Python using this F symbol in front of a string. What it allows you to do is for any string inside of quotation marks that's treated as actual Python code, and it'll get run. Once that's done, it'll put the whole thing together into a string. Which means, if I were to run this code, and then call something small like fib7, you should be able to see that all the actual calls, right, all the actual numbers are being printed out. So this allows us to see something interesting. If we were to call something huge like fib20, you can see how much work your computer is actually doing. But not just the amount of work. What I'd like you to take note of is also how often certain calls of fib are being repeated. You're seeing a lot of fib1s and fib2s and fib3s. These are being recomputed every time when it's not strictly necessary to do so. That's where memoization comes in handy. As you can see, it's still going, and I've already had to cut it a little bit, so I'll go ahead and stop it here. And I wanted to talk to you about an alternative way of actually looking at the number of steps, which will also come in handy when we try to actually write out our solution at the end of the day. This is a technique known as higher order functions.
This next topic, which is higher order functions, is not strictly something we talk about at the same time as memoization. I'm introducing this topic here because we're going to use these techniques to help us later on down the line, but of course there are many other ways in which you can do memoization. But anyway, here's the idea. A standard first order function will take in some data, do some processing on that data, and then return it. So all that flows in and out of that function is, well, data, variables, information. But when it comes to higher order functions, it does more. A higher order function could potentially take in functions as inputs. It could do some processing, including constructing functions on the fly, and then returning them. So a higher order function is like a meta function, so to speak, because it can actually take in and manipulate functions, potentially even returning new functions. And that's exactly what we're going to exploit. Before we jump in to write the code, let's just take a look at a big picture of how we're going to approach this. The idea is this. You have your recursive function, and at the end of the day, we want to implement memoization to your function, right? So how we do that is we take in your function, we inject some code that does the memoization logic. Of course, we can't modify your original function. That's already done, right? But what we can do is we can build a new function that wraps around your function. Our function doesn't just call your function, it goes through the memoization logic first. If required, it calls your function. This new function is then returned. And what you need to do is to replace your original function with ours, with the augmented code, the augmented logic inside. And that's how we basically add some additional capability to a function that someone else has written. So let's start simple. Before we talk about memoization, because we haven't really defined that yet, let's try and just count. Let's just see how bad Fibonacci actually is by injecting a little bit of counting logic. This, of course, is also a good opportunity for you to get used to the entire pattern of us taking in a function and augmenting it. So let's take a look.
Here's how higher order functions can help us. What I'm going to do is I'm going to create a new function here called count. This is a special function because its input, its parameter, is going to be another function. You can expect what this function is going to do is it's going to take in f, which is another function, it's going to modify it a little, and it's going to pass back the modified version. Let's see how this works. Now, we want to implement a counter, so we're going to do it in the most simple, straightforward way. It's not great, but bear with me. I'm going to create a variable here called numSteps, and it's going to start at 0. And now what I'm going to do is I'm going to create an augmented function. So this is a version of f that has been augmented with some counting properties. Now, because this is an augmented version of f, it's going to need to take in the exact same parameters as f does. I'm going to just write this out as it is. We're going to see its power later on down the line, okay? But I'm essentially going to write asterisk params like this. In Python, the asterisk means that we don't know how many parameters there are here. There could be 0, there could be 10, we don't know. And the good thing is we don't care. By writing it this way, params becomes a tuple, which contains all the parameters, all packaged together nicely. Let's not worry about that too much for now, right? Let's just take it that this is doing the right thing, and let's go in and start to augment the function. Here's how we're going to do it. Essentially, fcount is going to be identical to the function f that was passed in, with the exception that every time we run the function, we're going to increase the counter by 1. So this needs to be done in 2 steps. First, I want to say global numSteps. And the reason why I want to say that is because otherwise I won't be able to modify this variable which is in the global scope. So this just says it's okay, I want to be able to do that, and then I'll increase the number of steps by 1. Okay, so every time this function is called, numSteps goes up by 1. Of course, this function alone isn't doing anything just yet other than counting. Ultimately, we still need to call the original function f. So f takes in all the parameters. We're just going to say take the parameters, unpack them, and then send them through to f. Of course, we don't just want to call the function, we want to also get its return value and pass it back. Alright, so this is the complete augmented function. What I'm going to do now is I'm going to go ahead and return fcount in the outer function. So I hope this is not too confusing, but let's recap a little bit. The function count takes in a function called f. It's going to build a new function called fcount, which on top of actually calling f, it's going to do an additional counting step as well. Once we're done with this definition, we're going to return the new function. That's the idea, alright? So here's how you use the count function. Since we already have a function called fib, let's go ahead and augment that. And we'll say fib equals to count fib. How this is going to work is fib is going to get passed in here. It's going to get augmented like this. And the answer that is returned, the resulting function, is basically identical to fib, except we've injected some additional logic to help it count with numSteps. So let's try it. I'm going to go ahead and run this code. I'm going to call, say, fib10. Oh, I forgot to take out the print statement. Never mind. So this is the answer of calling fib10. But what I can do is I can try to print out the value of numSteps, and you can see that the answer is 177. So fib10 took 177 steps to get to the answer of 55. We know this because we know that every step we count up by 1. Okay, so that's how this actually works. Of course, there are a couple of caveats to this technique. For one, you won't be able to count across multiple functions because there is only one numSteps counter unless you go to the trouble of resetting it yourself. And on top of that, you have to be careful to actually overwrite the original function with the augmented version. Because of course, the original function is just going to look for a function called fib and then call that. So if you call this a different name, this will end up calling the original function. So these are the 2 caveats you need to worry about. But otherwise, we essentially have what we need. If I were to just go ahead and take out this statement and then rerun the whole code, which also at the same time resets numSteps, I can now call fib of anything. Let's do fib30. It's going to take a moment. We're going to get our answer, but we're more interested in numSteps here, which turns out, yeah, pretty huge number, 2.6 million steps just to compute fib30. We can do better.
I think we're finally ready to talk about memoization, so let's get into it. The big problem with the Fibonacci function is that it makes a ton of recursive calls. That's what makes it slow. But what's even worse is that if we take a close look at the recursive calls that, well, it's making, you realize that we don't even need to do that. In fact, we keep making the same recursive calls to the same Fibonacci functions that's gonna have to, well, do a lot of work just to give you the same answer you've already seen previously. That's why this comes up in dynamic programming, right? It's overlapping subproblems. The concept behind the memo table is this. If we know that a particular function call is going to give us a particular answer, then after doing it once, we know the answer. We write it down, we take note of it somewhere, so that if in the future I try to make the same recursive call, don't actually do it that slow. Instead, go look it up. We already have it written down, and looking it up is much faster. That's basically what a memo table is. So yeah, I hope that concept itself is not all too difficult to understand, but you do need to take note of some important assumptions that we're making here. Firstly, each recursive call cannot have side effects. That means if each recursive call actually changes some other variables in the environment, then we can't just take shortcuts and not do certain recursive calls, because of course, those variables are going to be impacted differently. So we've got to be careful about that. No side effects means that every function can only take in information via its parameters and give out information via their return values. There is no other access of data, from the side, hence the name side effects. This also guarantees another thing that we are kinda assuming, which is that for any given function call, for any given set of parameters that you give it, the result is always consistent. That is, let's say, fib5 will give you one answer now, and no matter how much later down the line it is, calling fib5 must still give me the same answer. If that does not hold, then of course the whole notion of memoization doesn't hold as well, right? I can't just take down a value I've seen before and use it later on, if later on it's going to give me a different answer. So yeah, these assumptions have to be in place first. Anyway, I think that's enough setting up the scene. Let's write code.
So it is now finally time to build our memoize function. And again, we're going to use the same technique of augmenting an existing function like this. Alright, so it's higher order functions all the way down. So let's create a new function called memoize. Memoize is going to take in a function as a parameter f. And of course, as usual, it's going to, build a new function, take in the same parameters as it, and then eventually return out the augmented version of the function. So the pattern here is the same pattern as this guy so far. Okay, so I hope you are familiar with the structure by this point. So let's go ahead and build our memo table so we can do our lookups. But here's the twist, we are going to cheat. Our memo table is simply going to be a Python dictionary. How a dictionary works is every value is associated with a key. So if you give a dictionary a particular key, it's going to give you a value. So instead of having a multi-dimensional table where sort of every index represents one possible parameter value, we're just going to take all the parameters and we're going to turn it into a string. So essentially each set of parameters, which is a tuple in this context, we're going to just force it into a string of text and then store it into a variable called key. Then all we need to do is check against our memo table. Now of course, this variable is again one in the global scope, so we've got to do the same thing as we did just now with num steps. Alright, so global memo, and what I want to do is I want to check to see if the key is already in the memo table. In other words, if we've called the function f before with the exact same set of parameters. If we have, what we'll find is that that particular set of parameters, which acts as a key in this case, already exists within the memo table itself. So if it does, then we'll simply return the value from the memo table that has that key. We've done that work before, we don't want to do it again. Alright, and the only time we need to actually do the hard work is if that key does not exist in the memo table. In other words, we've never called that particular instance of the function before. In that case, we have no choice. We will need to call the original f with the params, but what's more important is that we need to get its answer back. Now, unlike this guy up here where we simply return the answer to the caller, we're not going to do that just yet. We're going to intercept the answer into this variable here, and what we're going to do is we're going to stick that into the memo table. Alright, and of course it's going to be associated with this key, which again comes from all the parameters that have been passed to the function, except now converted to a string. Alright, so what we've done is we've updated our memo table. For this set of parameters, this is the answer you're going to expect. We already know this, so that for future calls, let's not bother doing the hard work again. That's the idea. Of course, ultimately, we do need to return the answer as well, right? So that whatever recursion can continue to run. So that's basically it. That is a generic memoization function in which you can pass any function to and it will memoize. So of course, all that remains to do is to try it. Again, we're going to do this to fib, and the syntax you're going to use is fib equals to memoize fib. Right, because we're going to take fib, we're going to put it through this function, which is going to modify it by augmenting it with all these features. Of course, fmemo will call the original f if required, and of course, ultimately, we get that back, right? So fib is replaced by the memoized version of fib. Now, I'm not going to try and do any counting just yet, right? I just want to run this code and see if it works. Now, if you remember previously when we did say fib35, my computer struggled a bit. let's try it again this time and see how quick the response actually is. It's practically instantaneous. In fact, what we can do now is even something crazy like Fib 100, and you get the result again in an instant. So that shows that we have had a lot of improvements, right? In fact, let's go ahead and measure exactly how much improvements have come about. So what we're going to do is we're going to double augment our Fibonacci function by taking the already augmented fib, and we're going to add the count ability to it as well. Alright? So bear in mind that this fib is not just the original Fibonacci function, it is the memoized version that we've created here. What we're going to do is we're going to wrap counting around it as well. Okay, so I'm going to go ahead and run this code, and I hope you remember that in an earlier clip we did Fib 30, and that took about 2-point-something million steps to actually compute. Let's try that again. We are now doing the memoized version of Fib. Let's do Fib 30. We get the answer instantaneously. But more importantly, if we look into the numSteps variable, you'll see it just took 59 steps. That's right. What took over 2 million steps previously has now been reduced to just 59. Hopefully that shows you the power of doing memoization. Hopefully that shows you just how inefficient the original Fibonacci function is, how much redundant work it actually does that it doesn't have to. With memoization, the same task gets done in just 59 steps. Again, I want to emphasize that the same caveats apply. A memo table here is sort of just a single global variable, right? So when you call memoize of multiple functions, then the two memo tables are going to clash because they rely on the same memo table. To work around this problem, both for memoize as well as for count, you'll probably want to do some kind of class-related method so that, each instance is basically augmented by its own class, by its own memo table, by its own count. I'll try and put together a version like that for download in the video description. Alright, but do take note of the caveats. Also, I think this is a great time to actually take a look at a memo table, right, just for you to visualize its contents. This is what the memo table looks like. So what you'll notice is that these are associations, right? There's always a key, colon, a value. And yeah, essentially these are all the values that Fib gives you, right? So the parameter here is 22. In other words, we're calling Fib 22. And the answer is this. So you realize that for a lot of these, right, Fib 5, Fib 6, well, since we call Fib 30, I think, yeah, a lot of these smaller values, they get hit very often. If we didn't memoize this, you realize that a lot of this gets recomputed. But with memoization, we save on a lot of work. What's cool about the technique that we've been using is that thanks to the fact that we have this asterisk notation, the user can basically enter any number of parameters and they all get packaged into a tuple. In order to appreciate how easy that makes things for us, let's think about an example. Let's say we call our function with 3 parameters, 1, 2, and 3. So params is just going to be a tuple that contains the 3 items. Then we're going to take the entire thing and turn it into a string. So key is just a string that looks something like this. This allows us to easily identify that 1, 2, and 3 are the input parameters required to create whatever answer we figure out later. If we call the function f later on with a different set of parameters, then it'll become a different key. Which means, yeah, we don't have to do much thinking at all. Things just work. No matter how many parameters we have, this technique holds true. And I think the easiest way to appreciate this is to just test this on a different function. So let's take a look at the binomial coefficient function, or also known as the combinations function, right? So out of n items, how many ways can I choose r items? Anyway, the math isn't so important. What's more important is the fact that now we have n and r. So we have 2 parameters. The recursive relation is defined as such. N or 2 base cases are when r goes down to 0 or when n goes down such that it is equals to r. Both of these will give you the answer of 1. Of course, n must be non-negative. So let's go ahead and implement our binomial coefficient function, or what I will call NCR. Alright, so let's define NCR, and of course the difference here is that there are 2 parameters now, n and r. So let's start by implementing the base case. So the base case is as follows: if r is 0 or if r is the same as n? In both cases, the answer is simply 1. So that's our base case, no more recursion required. Else, our recursive case is a little bit complex. Essentially, this is the sum of n minus 1, choose r minus 1, add that to n minus 1, choose r, so the same r. So again, like Fibonacci, every call to NCR could potentially create 2 more calls, and those in turn will create 2 more calls, and then you get this explosion of steps. So what I'm going to do, right, is I'm going to go ahead and just augment that using count alone. So we can take a look at how bad this gets. So NCR equals the count of NCR. Alright, now we can run the code. And let's do NCR, something a little bit more challenging, say 20, choose 8. So when we run this, well, it takes a short moment. Let's look at the number of steps. Right, 250,000 steps. So you can see that it's by no means efficient. Let's go ahead and do memoization. So NCR equals to memoize NCR. And when we run the same code, let's do 20 choose 8 again. Right, so NCR 20 and then 8. And then let's look at the number of steps. Now it's just 193. Thanks to memoization, yeah, we've shaved 3 digits off this number. So that's pretty good. Of course, the purpose of this particular demonstration is to show you that our technique here is generalizable to a function of any number of parameters. So let's take a closer look at the memo table that has been generated here. Let's see if we can digest it a little bit better. Now, you realize that this right off the bat looks a lot more complex, right? The keys, which are of course tuples, now contain 2 values, not just 1. And of course, the reason for that is we've got n, we've got r, so we need to keep track of both. And what this particular key means is when we call 10 choose 3, the answer is 120. Later on, we could potentially call 11 choose 3, which will give me a different answer. I could call 10 choose 4, which will give me a different answer. So now this becomes sort of 2-dimensional because there are 2 values that could possibly change. Thanks to the fact that we are using the cheat method, which simply puts the 2 parameters together as a tuple turned into a string, we don't have to worry about that 2-dimensional structure. We could easily have a 6-parameter recursive function and the right thing will happen. So again, that's the power of this technique.
And there you go, that's memoization in a nutshell. And what's nice is the augmentation method, because now, for any given function, and as we've seen, no matter how many parameters it has, it's okay. All we need to do is to fit that through our augmentation. Our augmentation will add the memoization logic to it, and then lo and behold, we have a fast, efficient memoize function. So yeah, that's it. Now, you don't have to do memoization this way, alright? You can always do this as a multi-dimensional array, where all the indices represent all the possible parameters that, well, you could actually give to your function. It's just that we're using Python. Python makes things easy for us, so might as well make good use of it. Anyway, that's all there is for this video. I hope you've gained some insight today. But until next time, you're watching 0612 TV with NERDfirst.net.